Thank you, Daniele, and thank you, the organizers, for putting all this together. I think it's very interactive for me. And thanks for inviting me. Okay, that's not... So I want to tell you a bit about, I'll continue a bit about how to compute with Spin-Wave Solitons. So in particular, I'll talk about collective excitations in spin-torque oscillators. So, well, we know what's a spin-torque oscillator. So we have an electrical point contact to a ferromagnetic thin film. And then if we pass a polarized current, we can exchange moment between the polarized current and the lattice magnetization. And eventually, we can create some type of excitation. So when we have an extended layer, the first thing that comes to our mind is to propagate spin waves. But we can also have vortices, and we can have solitons. I'll tell you a bit about droplet solitons. And actually, we can also have dynamical skyrmions. So these are all dynamical excitations of the magnetization. So Johan gave a good introduction, and also Axel on dynamics of the Landau Lifshitz. How do we describe the magnetization dynamics? This is important because this is telling us all the potential of these oscillators to me in neuromorphic computing. So if we forget for the moment of this term, this is the damping, dissipation, and this is the effect of the applied current, a polarized current. We basically have an oscillator. So this oscillates around the effective field. And the processing frequency is just the value of ms, let's say, times the effective field. But the effective field depends on the applied field, external, so we can control the frequency of those guys. And then we also have many more terms, but I just list two here. One is the Dirac field, so dipolar fields. This is non-local, and also exchange fields. So we've seen it before, but if we change these, if we change the magnetization, the amplitude of the oscillation, we are changing this effective field. That means that we're changing the frequency. So those guys are nonlinear, and they can be tuned by any of those parameters. Of course, you can also tune it by the current. So if you change the spin transfer torque, you change the amplitude. And if you change the amplitude, you can change also the effective field. So these are tunable oscillators. This is a key part also for synchronization. So if you want to synchronize, they have to see each other, and they have to interact, and they have to be able to change the frequency of the other one. So if they have Dirac fields or exchange fields, so that's one way you can do that. Okay, we've seen this picture maybe 4 times already, but I won't go into detail, but there's just one thing that I felt that just in the last talk, maybe I just want to say that here we have 2 oscillators with different frequencies, and then suddenly they jump into a locked state. That means that they have the same frequency, but they might have different phases. Not different, I mean a relative phase between the 2. So at some point, they might have the same phase, but when you have 2 oscillators that are synchronized, they have different internal frequencies. So when they see each other, they merge into the same frequency, but the phase depends on the strength of the coupling and the distance of the internal frequencies. So actually, this is something that it's tunable. So when they are synchronized, you can change the internal frequency of one of them, for instance, applying a current to one of these guys, so you shift the internal frequency, so they are still locked, but you might change the phase. So that could be some of the tunable parameters. We didn't see that, but you can also do synchronization of vortices in spin-torque oscillators. So here, instead of spin waves, the coupling is through an anti-vortex that it's processing around the vortex. So here it comes what we're talking about. So bio-inspired computing. So can we use the waves and the spin-torque oscillators to do what? So we know that the brain, apparently, it has fewer units the scale is much larger than what we work, and also, I mean, it works at kilohertz. It's not even true. It works at tens of hertz. And however, there's a few things, or many things, that the brain can do much better than a computer. Not all, but some of them are. For instance, pattern recognition or solving some kind of algorithms. So then the question is like, what is making the brain powerful? So here I'm just listing a few things that are, let's say, relevant to the work I want to show you. So it has many connections, right, compared to a normal computer. And also it works with delays, which is a quantity that's non-digital, so it's an analog quantity. And also the synchronization seems to play an important role. So in many brain activity, what happens is that there are groups of neurons that get synchronized for particular tasks. So a normal computer has a unique clock, right? So nowadays, I mean, it's working at gigahertz, so it's quite fast, as I said, compared with the brain. But it's a common clock, so every time that clock ticks, so there's a single operation. All the transistors can fire together. However, neurons don't fire together, so they can get synchronized, and they can get different clocks indeed. So that's called polychronization. And that, in principle, can give us ideas on how to use it to get away from the normal computer scheme. So we know there's a lot of work on neural networks, and mostly on working with artificial intelligence and software, but I think that we're mostly interested in getting some physics realization or solid-state physics realization. So what I believe we need is like, okay, we need oscillators that work as neurons, but they should be signal emitters, but neurons are also receivers, right? So when they get super threshold, they can get fired. So we need elements that work as emitters and also as detectors. We might need a media as well to get these emitting and receiving signals, and also the synapses, which are functional connections. So it's not only that you get the connection, but you can get weights and you can use functions there. So the Spintronics oscillators, actually what they provide is like we have oscillators at the gigahertz range, probably hundreds of megahertz for vortices. They can emit spin waves. We'll get into that part. And they can be used as a microwave detectors as well because of the GMR and TMR. And actually they can also be used as a memristors in some cases. I'll tell you when. So this is an example of the importance of the delays. So very simplified, but this is how we can tell where some like noise or sound comes from there or there. So we have two detectors, and there's a delay. When the sound comes from there, there's a small delay here, and what happens is that we have a detector, which is C. We have many detectors, and then if they come from the same place, so if it comes from there, there's no delay. So C is not getting a super threshold. Whereas if there's a delay, let's say 15 milliseconds, then this detector is telling me, yes, it comes from there. So I have an array of detectors, and then I can tell where the sound comes from. So this idea can be implemented with wavefronts. So these are electrical signals connected through axons and synapses, but here you can do the same. So if you have two-point contacts that emit spin waves or waves, basically if they fire together, you will have that they have a super threshold or they have an interference right at the center. Whereas if one started before the other one, this one was first, then the delay will make that the interference occurred at a different place. So one possible structure you can do is like you put several detectors here, and then you have two-point contacts. So these are the inputs. So if you can create a spin wave or a wave, then depending on the delay, you will have a super threshold in a different detector. So that's a proposal for a delay detection. So this is in this pattern in general for waves. And in here is just an application for spin waves from spin-torque nanocontacts. So this is a very theoretical part, so we'll go into the experimental parts, but imagine that we have this just a simulation of a spin-torque oscillator with no defects, no effective fields from, let's say, no Ørsted fields. So you can create isotropic radiation patterns. But when you combine spin-torque oscillators, you can have interference. So with interference, you can enhance activity in particular directions. But the question is like, but can we control this spin wave emission? And the answer is yes. So this is like dipolar antennas that they interfere, so they cancel activity in some directions, like here, and they enhance it in others. So we can control that actively just changing the phase between the two oscillators. And this is doable, as I told you before, because you can just change the frequency of one of the oscillators, and if you change the frequency of that oscillator, you're changing the phase when they are synchronized. So if you change the relative phase, then what happens is that the radiation pattern that you're getting is totally different, because the interference occurs at different positions. But this is what's been measured. So we don't have isotropic radiation so far. So this is a work here, the first one, and it was seen that with micro BLS, you have a point contact, and you see mostly the spin wave activity is perpendicular to the applied field. We also measured a similar experiment with X-ray microscopy, and actually we saw kind of the same. So we were able to see beneath the contact, but the idea is the same. So this is the spin-torque oscillator, and instead of having the radiation everywhere, which it's probably there at a higher order, all the spin waves are localized in a particular direction. This is because just the effective field, so you have a landscape of effective field, and that focused on a particular direction. So here we have a combination of Ørsted fields plus the dipolar fields of this guy, because this is a pattern fixed layer. So I've seen there's also, Sergey had a nice poster there that shows that there's means to direct spin waves, which means that in principle, maybe the isotropic case, it's difficult to reach, but there are ways to direct spin waves. So in principle, one could think of using them as for wave computing. So now I switch to solitons. So these are different kind of spin waves. So these are, you can call it kind of condensate. So it's just like spin waves do not propagate in certain cases. So let me just go back to the Landau-Lifshitz equation. So if we forget about the damping for a second, so solutions of these, of course, there's the FMR, so they are all processing in phase. But if we get a magnetic material with uniaxial anisotropy, one of the solutions of this equation is also this, having a droplet where all spins are processing inside. The frequency of this droplet has to be a little bit lower than the FMR, so they don't propagate away. There's no K vector available, so they stay here. So these are solutions of this equation. Of course, in reality, we have dissipation, so in principle, we don't see those objects. But in a spin-torque oscillator, we can cancel locally, but we can cancel the damping, so that these solitons should appear. So that was a prediction that if you cancel the damping in an electrical contact, you should see, this is a simulation, you should see the reversing and precessing. So this is an oscillation. It's not only a droplet like static, it's a precessing object. There were proposals later on showing that if you manage to get that and move them away from the nanocontact, of course, they might decay, but they can interact. And depending on the frequencies and phases, the relative phases, they might interact doing, for instance, this, going out there, or just reflecting. So they could be also used for wave computing. So what's been measured here? Well, we have a spin torque oscillator, we have a free layer where we try to see the excitations. So the droplet, what does is just it reverses completely the magnetization here while processing. So there's two ways that easily you can detect that. One is that looked at the DC resistance and the other one is the AC resistance. So just using a normal scheme that is used in a spin torque oscillators, we can look at signatures of droplet nucleation. So that was the first one in Johan's groups. And so there's a clear sign, there's a jump in the DC resistance and a change in the trend. And also you can see here there's the FMR there, maybe not visible, but then suddenly there's a jump to a lower frequency. I told you it's important. If it was higher the frequency, you should get spin waves. So you get lower frequency, and that means that it's localized there and much higher signal. Later on, we measured the similar object on different devices, and we found that they are quite stable and they showed hysteresis, both in current and magnetic field. So this is important because it shows not only that they are very stable objects, but also that they can be used as the memristors. So you have two resistive states, and actually you can stay in one and tune it either with applied voltage or current. So you get a different resistance state. And these are the images. So here it's, I think like experiments are not that far from the theoretical predictions. And we can see that in most of the cases where solitons were imaged, they have a very localized area. And in some cases, it looks like they're a little bit bigger. What else? So those guys, different from a normal spin torque oscillator, this is very localized and depends on the effective field. And the effective field in a film that has like not noise but different grain sizes maybe and different anisotropies, what happens is that you have an effective field landscape. So when you have that, what we see is that you have different oscillations. So you have different states of oscillating. Actually, let me show it here. Maybe it's more clear. There's 3 states there. And actually what we see is that if we apply a magnetic field, when the magnetic field is large enough, we jump to a single oscillation state. But when it's low, we have several oscillation states. So we simulated that and putting different wells, small wells on the landscape of the orders of millitesla, we can manage to get that the localization of the droplet is in different places. So when you apply a larger field, what happens is that you change the landscape and suddenly it jumps to another one. And actually all those different states, they correspond to different DC resistance states as well. So one more thing is like this could be useful for some applications, but there was a similar object to the droplet, which was called Dynamical Skyrmion, and this is basically the same idea, but a magnetic droplet, it's a continuous deformation of the, let's say, uniform magnetization state. That means there's no topology there, whereas the magnetic skyrmion has a topology. So that was predicted to happen in films that has DMI. Well, with DMI you can stabilize it, but it can also appear without DMI. Oof. So here we show, I mean, we looked at the conditions that you need to create these topological states. So these are processing. These are not static skyrmions. So the magnetization is processing all the time at the gigahertz. And here, for instance, we show the difference between a droplet state and a dynamical skyrmion. So droplet state jumps from one state to another one, as I told you. So that could be useful. But the dynamical skyrmion prefers to stay in a single state. So it's topologically protected, so it's more stable, so you can have a single oscillation rather than multiple oscillations. So finally, there's just one missing object I wanted to tell you a bit about, which is the vortex oscillators. So there's a lot of work done on that in pattern recognition, I think in Julie's group and other people. But here I just wanted to show you that there's a great resemblances between what happens when you synchronize an array of those oscillators, so that can relate also to Johan's group, where you have like arrays of many oscillators connected. So here we looked at let's say, it's similar to that. So it's a two-dimensional array of spin-torque oscillators. And here they are just coupled by dipolar fields. So we didn't allow any exchange fields. So these are just patterns. This is simulation work. And what we did is to compare like a micromagnetic simulation, taking all the ingredients into account, and trying to see what happens, what we can do just by calculation. So by calculations, we took the Thiele equation. The Thiele equation is just a simplification of a micromagnetic or a macromagnetic model for the whole object into a very single equation that tells you how it moves the vortex. And from that equation, we put some extra coupling between different oscillators. And actually what we obtain is that we get the Kuramoto model. So the Kuramoto model is a very simple model for synchronization of that is used in many fields, but one of the fields it's used is to describe the synchronization of neurons. So what we find is that this is what we expect from the Kuramoto model, and this is the micromagnetic simulation. So it fits very well. And actually another nice thing is that when we use the Kuramoto model, it is well known that you can start getting a lot of, let's say, patterns in the phase space, in the neurons. And here we see the same. So these are micromagnetic simulations, and when we change the strength of the coupling, that means changing the distance between the spin-torque oscillators, so this is 1 over the distance, what happens is that when they are far away, there's no synchronization. And when they get synchronized, what happens is that if you looked at the phases, you see that there's a map of phases, and in between, you can get all those patterns that are phases. Okay, I don't want to get into details. So to summarize, I just went through some of the collective excitations in spin-torque oscillators. So I tried to give you some ideas of how can they be used for wave computing. So now I'll be happy to take any questions or get into anything else. Thank you.